First topic, we'll start from measurement and errors. Okay, now this topic is the easiest topic in the whole physics. Okay, so we'll start with the term called what is called as least count. Right, let us say that we have a scale. Okay, 1 2 3 4 5 6 8 9. Okay, starting from 0 1 2 3 4 5 6 7 8. Let's assume this is a scale, normal scale, right? And let us try to use this scale to measure the length of a pencil. Okay, this is a pencil. Now if this is, I'll write in centimeters, so this is cm to 8 cm. We are very familiar with the length measured using centimeters. Okay, now what is the least count of this particular centimeter scale, right? So that is least count in the sense, what is the minimum length that you can measure, right? This is minimum length that can be measured, right? In this case, only in this case, that is example, right? 1 centimeters, right? So what is the minimum length that you can measure exactly, right, without any mistakes? Right, now you see, if I say this answer as 6, then that is wrong, because it's more than 6. If I say this length of the pencil is equal to 7, that's also wrong, right? Because since I don't have any facility to measure between that 1 centimeter 6 to 7, right, we are able to count the right values not accurately. Okay, so that's why it leads us to an error. That's the first point, right, to remember in the measurement and errors, right? Then we'll define something else. This is significant figures. Okay, so significant figure refers to something very specific in this, in the concept of measurement. When we go for measurement, we should know what exactly is significant figures. Okay, now let's define. Okay, this is in a measured quantity, so the significant figures are the digits which are absolutely correct, plus the first uncertain digit. So This is what is called as significant figures. So if I give an example, let's go for an example of this. So let's say that I measure length is equal to same 6.5 centimeter. This implies, so I'm very certain is this zero point 0.5 is uncertain. Uncertain digit 6 becomes the certain. Okay, so totally you see that the significant figure, I'll just write SF is equal to 2. Significant figure in this number is 2. Okay, we'll discuss about the different rules to be followed, that's coming up. But just to define, if I give another example, L is equal to, this is 3 point, say 267, maybe, once again centimeter. This implies the significant figures in this case is equal to how much? This will be 4. So if I say x, some value x is equal to 126.28, right? Doesn't matter which unit you use, right? This is something else, x. Okay, maybe velocity, right? In this case, the significant figures is equal to 5, and so on. Okay, we can calculate in the same way. Okay, let's go ahead. Now, what are the rules to be followed? What rules we have to follow in order to, right, calculate the significant figures? This is important. Rarely we can see some questions based on the rules. Okay, fine. The rule number 1 is all non-zero digits are significant, right? In the sense, take an example of the previous uh, case, 126.28. We had counted all the non-zero numbers that are present in the number as significant. Okay, that's the best example. Now let's go to the next point to be followed whenever a question comes on the significant figure, right? So if you have the zeros appearing, between, okay, two non-zero digits, two non-zero digits are also significant. Okay, if you get a zero in between two non-zero numbers, non-zero digits, that is also important. For example, I need to consider the zero which is present in this number, right? So in this case, what is significant figure, right? We know that all non-zeros are significant, so definitely 6, 2 and 5 are significant for us. But there is a 0 between 6 and 2. This means 0 appearing between the two non-zero digits are also significant. Okay, so in this case, the uh, significant figure is equal to 4, not 3. Okay, next, this will be the rule number 3 for counting the significant figure, right? The powers. Okay, the trailing zeros. The trailing zeros after the decimal after the decimal place, okay, are significant. Okay, for example, if I write, this is very important rule, if I write L is equal to 6.4000 centimeters, right? This rule says that after this decimal point, right, if you get some zeros, right, they are also important, they have to be considered. So the significant figures in this case is equal to 1 2 3 4 5. Okay, after the decimal place, whatever zeros will come, we need to count that. Okay, then this is the next rule. The next rule is powers of 10, right? If you write a number as into 10 to the power, we'll see what happens. So power of tens are not counted. They are not counted in SF. For example, if I write 1.4 into 10 to the power minus 7, right? So what is the SF? Significant figure is equal to just 2, 1 and 4, not the 10 to the power number. Okay, right. Then the next point is this. If the measurement is less than 1, okay, if the measurement is less than 1, then you see all the zeros occurring to the left of the last non-zero digit. Last non-zero digit are not significant. This means, for example, let's take the measurement L is equal to 0.0042, right? In this case, the last non-digit number is this 4, right? Before 4, how much ever zeros that may come, right? They are not significant. This implies what is a significant figure in this case? You can see that SF is equal to 2. Only 4 and 2 will be considered. Okay. Now you can see that this is because irrespective of the way you write the number, right? Irrespective of the way we write the number, right? We have to have the same significant figure throughout. Okay, let's take another rule to make the points very clear. So change in units of measurement of a given quantity a quantity does not change, doesn't change the number of significant figures. Number of significant figures. So for example, let's take an example to understand this. Say if I write 7.2, okay, let me write this as centimeters, right? What is the SF? In this case, I know that SF is equal to 2. Okay, now let me convert 7.2 centimeters into meters, right? Into meters means this is 0.072 meters. Okay, this means what is the SF in this case? This is also, in this case also it is 2. See the same number, right? 7.2 centimeter became 0.072 meters. All right, then let me convert this into say kilometers. So that is 0.000072 kilometers. As per the rules, we already know that the before the last non-zero, whatever zeros you have, they are not significant. So once again, I have SF is equal to 2. Okay, and so on. We can expand this to any larger numbers, and you can see that the SF will not change. As far as the given quantity, we are following the rules of that. It will not change, right? The total significant figures. It still remains same. And we have another point to remember. The terminal, or it's actually also referred as trailing zeros in a number, without without decimal point, without decimal point are not significant. They are not significant. So this is important, right? Which means, right? For example, let me say this is 264 meters, right? This implies what is the SF? By default, this has to be 3. SF is equal to 3. Okay, let's write this in centimeters now. That means I have to convert 264 into centi. Centi is 2 zeros. cm. So without a decimal point, now I don't have a decimal point, right? That's why these two zeros needs to be neglected. I still have SF is equal to 3. Okay, and even if I convert this into a different unit, say millimeters, that means 264,000. This is millimeters. You can see that this is going to have a SF still equal to 3 because these two zeros and these three zeros do not have any significance when we represent that. All right, let's go ahead and go for a last rule to be remembered. So exact measurements have infinite number of significant figures. This is also important, right? So for example, if you write pi, value of pi is equal to 22 by 7. This is the exact value. So this is expected to have infinite number of SF. And say the number of students in a class, we say exact representation. I know that in my class I have 50 students. So that also is going to have the since the measurement is exact, you can say that it has infinite number of significant figures. Okay, right? Anyway, this last point is not applicable for all the cases. All right, let's go for another example. This is 1.60 into 10 to the power 40. So perfect. So we have value of s uh, is 3. Now we'll consider the set of rules for rounding of a number. Okay. So basic rule we already know. If you have something more than 0.5, you make it to the next number. Less than 0.5, you make it to the previous number, and so on. Okay, but actually we have many rules in physics to be followed to make our measurements accurate. Even though we try to round off something, rounding off actually is introducing error, right? But you do it in a controlled way. That's why we need to follow the rules. Fine. Rule number 1. Right. If a number is lying to the right of the cutoff digit is less than 5, then the cutoff digit is retained as such. If it is more than 5, right, you are going to increase it by 1. This is a rule which we know already. Okay, I'll write that, but as this is a specific rule. Okay, so this is if a number lying to the right of cutoff digit is less than 5, right? Then the cutoff digit is retained. Okay, is retained as such. Okay, and the next thing is that in the same point, if that digit, I write it is more than 5, right? Then the cutoff digit gets increased. Okay, increased by 1. So let's go to the example. We know this. So let's say that x is equal to 6.24 and I want to keep two significant digits, right? If you want to keep two significant digits, I need to eliminate the 4, right? When I eliminate the 4, I look for this rule, right? 2 is my cutoff. After 2, I don't want any digit to be present. So what do? You look at what is present, right? And after the cutoff is. Now it is 4. So as per this, it is less than 5. Less than 5 means it is retained as it is, right? Can be rounded off to, right? 6.2 itself. We know that. Let's go for another example. Say y is equal to 5 point. This is 328. So this means I want to, let's say I want to retain 3, right, significance figures. So this means uh, 3 in the sense 5, 3, 2 should be considered. I look after 2, it is 8, which means this is more than 5. More than 5 means cutoff digit is increased by 1. So 2 becomes 3, that's all. Okay, so this is 5.33, straightforward. All right, let's go further. The rule number 2. The second rule is, if let us say that the digit to be dropped is 5, okay, and it is actually followed by digits other than 0, right? Then the preceding digit gets increased, all right, by 1. I need to increase this. This is also very well known fact, so let's go quickly about this. This is x is equal to 14.252. So you want to retain 3 SF significant figure, in the sense I need to look at 2. After 2 I have a 5 followed by 2. So this rule is 5 followed by digits other than 0. So now 5 followed by 2, which is other than 0, which means your point should be increased by 1. That means 14.3. Okay, now the next rule is this. If the digit to be dropped is 5 or 5 followed by zeros, 5 followed by zeros, okay, then the preceding digit is unchanged if it is even, okay, and is increased by 1 if odd. So when you have 5 followed by zeros, right, you just have to check the previous digit. If it is even, keep it as it is. If it is odd, you increase. All right, very important. This we are not following usually. Okay, so say x is equal to 6.250, and I want to keep two significant figures. In that case, 5 and 0 should be eliminated, right? I look for what is the previous digit. Previous digit is 2, which is even. So this means you round it off to just 6.2 itself. You are not going to make it 6.3. Okay, let's go for another example. Say y is equal to, I'll write the same thing, 6.35. This means I want to keep, let's assume I want to keep the SF equal to 2, right? So significant figure 2 means I need to eliminate 50. So 5, before that I have an odd number 3. This becomes now 6.4, right? This is what is the important rule while coming to the rounding off of the numbers. Moving on to the next concept. This is we want to look at the algebraic, sorry, this is algebraic operations with SF, that is significant figure. What happens to the significant figures when you perform, right, algebraic operations such as addition, subtraction, multiplication, division, etc. All right. Okay. Now, for addition and subtraction, we have same rule, so we'll club them together. Okay, we can go faster in that case. That's why. So first category is addition and subtraction. Right. Now the rule is like this. So in a measured value that you want to add or subtract, right, the least number of digits after the decimal, right, itself will be the, right. So the answer should also be with the same value. I'll write first. I'll write. So in a measured values to be added or subtracted. Okay. Say the least number of digits after the decimal is, say, n. N is the minimum number. Nanತರ 4 number ಇದೆ. So we have 4 numbers out of which the minimum point decimal points is n. Right. So this implies in the sum or in the difference, right, the number of digits after the decimal must be n itself. For example, let's go to this. Let's say I want to add the 4 numbers like 1.2 plus 3.45 plus 6.789, right? So we know that if we are not having sufficient number of zeros, you can add zeros like 1.200 plus 3.450 plus this number, right? We'll add in a normal fashion. So when you add, what do you get? You get, I think we get 11.439 is my answer. But I have to find out the least number of digits after the decimal. In that case, that is equal to this number. This is 1 digit because this has 2 digits, 3 digits. So out of which is a smaller number, 1. So that means even in my answer, I have to keep only 1 decimal point. So after the 11 point something, it has to have only 1 digit now. So apply that rule, go to the next number is 3, right? Since that 3 is lesser than 5, keep the numbers as it is. So this is, right, rounded off to 11.4 because the rule says keep the minimum number of digits. Okay. So when we 2.43, but right, since I want to keep the number of digits after decimal point should be equal to the minimum number of points. Minimum number of points in the given numbers, that is 12.63 and 10.2, is 10.2, which has only one digit. So that means I need to make round off like 2.4 itself. Perfect. Right. After this addition and subtraction, now we'll go for the rules corresponding to multiplication or division. Now, in a given number, let us say that the least significant value I need to consider. Okay, so let me write the same rule. In the measured values to be multiplied or divided, let the least number of this is significant digits be n. Okay, then the product or the quotient, should have n significant digits. Okay, for example, I want to perform 1.2 into say 36.72. Straightforward answer is 44.064. Now it says that minimum decimal digit in this case uh, is possessed by 1.2, that is equal to 1. So I have to keep only one decimal point after this. Right, so in order to keep one decimal point, I have to look what is there after that. It is 64, so so after 0 I have 64, so approximate this to 44.1. All right, this is the rule number 1. And if I want to write say division 1101 divided by 10.2, what is this? This is, I think we get 107.9411. So you need to approximate to one digit, that is 9. After 9 I have 411, so which means it's kept as 107.9 itself.